what we want to discuss now is how in general we can predict the number of solutions or the structure. How in general we can predict the structure of the solutions by looking at the row echelon form. So without even going into the detailed back substitution, by just looking at the row echelon form, you already can predict what kind of structure of the solution you will have. And that's what this analysis of the solution section in your lecture notes is about. I copied these three matrices from the lecture notes, so you don't have to copy that. It's from the page 12, please. If you go to the page 12, on the page 12 you have three matrices, only three matrices. So all of these three matrices are here. So first one is like this. And we have to answer the question how many solutions this kind of system has. This time I don't ask for the exact solution, what the solution is. All I'm asking for is like how many of those we have. If you think through the way we go after the solution, we have to do back substitution, right? The back substitution associated with this system is here. I'll open it all at once for you. It's here. That's the system which is associated with this matrix. Let's just look at this. Now, this is a perfect triangular shape kind of system, right? Everything present, everything in a perfect triangular shape. So we know from practice, we practiced this a few times with you, this kind of system is solved uniquely. There will be one unique vector which gives us the solution. Good. Now, the second matrix on that page 12 is this matrix. It's like the one before. But now 2 is gone and now 0 in here. If we try to back substitute this system, that's the kind of system we will be looking at. Yeah, and I already feel the reaction here. The last equation turns into 0 equals 7, something nobody believes here in this class, right? Real numbers, of course, this never happens, and the judgment, our assessment of the system will be we cannot possibly back substitute it, right? Good. And the last example which on that page is the matrix like this. Again, first two rows are identical to the previous two examples, and the list times 7 is also gone, 7 is also vanished. This time the system which is associated with this, in fact, we'll have only two meaningful equations, right? Like this. Because last equation will be 0 equals 0. I didn't do that. Actually, I wrote this. 0 equals 0. Now, when you back substitute this system, what will happen? It's something we did twice today. We have to take the unknowns corresponding to, because we have pivots here, right? One pivot. It's another pivot. That's all pivots we have. So this column, in fact, is non-leading one. So the variable, which is x3 in this case, which corresponds to this pivot, must be parameterized. And we will end up with multiple solutions, the whole line of solutions, right? These three examples, they are the other one. It's crucial examples because they describe the nature of everything which might happen with the row echelon form. And every time when you look at this, you can judge by, you can always judge things by how many, look at this, if I single out all of these pivots for you, here we have 3 pivots. What about here, this matrix? How many pivots here we have? This is one. This is the other. Is that it? There is another one. This one. Technically, it fits the description of the pivot, right? It's the number, non-zero, and such that it is further to the right as the first non-zero number in the row above it. Now, in here we have only 2 pivots. Now listen to the general description now. I think you will now appreciate it very well. It's called a theorem, and it says this. It's in your lecture note. I just restated for you a little bit. It says this: if I have matrix, augmented matrix, and if I made an effort and I brought this matrix to the row echelon form, it will be something like this. It's some symbol which represents my row echelon form. These dots, they stand for some wisely chosen set of elementary row operations. Every time you start with the augmented matrix, if you proceed in a smart way, you will come up with some row echelon form. Now, by looking at this row echelon form, you can say how many solutions your system will have. And look at this, what we will have, how we can assess that. This system of linear equations associated with A and B has, here's the options we have. It has no solutions if the right-hand side is a leading column. That's the kind of thing which happened here. The right-hand side here happened to be a leading column, and that's a clear sign of the system not having any solutions. And that's a general statement which you can now use. Second, it says this: if your right-hand side is not a leading column, so it's one of these cases, either this one or this one, then you will have some solutions, but still you have some ambiguity. You have to judge how many one unique solution or multiple solutions, and look how we can judge that by looking at the leading columns. You have two options here, A and B. You have a unique solution if and only if, double F means if and only if, every column in the left-hand side, on the left-hand side is the leading one. That's the kind of thing which happened here. Every column, look, you see, every column was the leading one, and that's why we had the unique solution. There wasn't any room for the parametrization. On the other hand, if you have a column which is not the leading one, you have infinitely many solutions if at least one column is not the leading one. That's the kind of thing which happened here. And the variable which corresponded to this non-leading column, we parameterize that variable. If you have more than one variable, you will parameterize more than one variables, and all of them will be parameterized. For instance, you will have, if you will have two non-leading columns, you will need to parameterize two unknowns, and you will end up with the equation of the plane, because something which is parameterized by two unknowns, it will be equation of the plane. The same way it was the line, like one of you suggested for one of the examples we did. All they're asking is that look at this given row echelon forms. These matrices are already in row echelon forms. We don't have to do anything. And tell me, and just describe the structure of the solutions. It's like a very simple problem now after we have the general description. For instance, if you look at this one, what your answer will be, what kind of structure these solutions will have? No solutions, because it turns out that the pivot ended up on the right-hand side. What about this one? It is a unique solution because every column here is the leading one, because every column has a pivot. 4 pivots, 4 columns, every column leading, we have a unique solution. Now for the last one, your answer will be the solution, the structure of the solution is, we have infinitely many solutions, and you can even say me more about the structure of the solution, because you know how many exactly non-leading columns we have here, right? How many non-leading columns we have here? We have one non-leading column. We have one non-leading column, that's the one which is the third one, and that's one non-leading column which corresponds to the parameterization, that would be my line.